Well, the answer here in video 3, the actual answer has to deal with the Earth's tilt of 23.5 degrees. It's this change of tilt of 23.5 degrees and its orientation towards the sun that will ultimately influence two drivers of the seasons, which is length of day and the angle of the sun. So when you look at this hypothetical axis tilt here, I'm not going to spend much time on it. This would be as if the Earth was tilted 90 degrees. And what we're arguing is depending upon how the Earth is aligned to the sun and how it's situated in terms of, again, here is the equator, here is the North and South Pole. This would be a hypothetical situation as if the Earth was tilted 90 degrees, and this is obviously not the way the Earth is. It is actually looks more like this. We're going to see the Earth. I'm going to go back to that slide here in a second, but the Earth is actually tilted not 90 degrees like in the hypothetical situation, but just 23.5. And when you look at this tilt of 23.5 degrees, you could see that there are key white lines on here, and in the lab you will be doing on the Sun Angle Lab, you will actually be getting familiar with the equator, the Tropic of Capricorn, the Tropic of Cancer, the Arctic Circle, and the Antarctic Circle. These are lines of latitude, and you will know more about this after going through the Sun Angle Lab. But the key thing to pay attention to at this point is that as the Earth's tilt 1/2 degrees, as the Earth moves around its revolution, it actually is the tilt of the Earth here is what is controlling seasons, not so much length of day. So the reason why on the summer solstice it could be warmer, even though we're 3 million miles further away, is that the Earth is tilted 23.5 degrees towards the sun in the northern hemisphere, and the southern hemisphere is tilted 23.5 degrees away from the sun. So in winter solstice, it's vice versa. It's the southern hemisphere tilted 23.5 degrees towards the sun, and the northern hemisphere is tilted 23.5 degrees away from the sun. During the equinoxes, at the sides of the orbit, it is the equator in the middle of the Earth that is tilted towards the sun. So during the equinoxes, the sun's rays are concentrated, and they tend to move depending upon what season you're at. And there's basically two types of sunlight that I think is important for you to see. And I'm going to go fast forward because I think this is important to understand. And I'm going to go back here in a second. But right here, the angle of this, I'm going to go back. The angle of the sun can be direct or perpendicular, or it could be oblique, less than 90 degrees. Depending upon where the sun is striking 90 degrees, if we know where that spot's at, we could actually determine what season it is and what time of the year. Whatever location is getting direct sunlight is effectively the spot on Earth that's getting maximum solar radiation. And the more oblique it gets at a lower angle, the more the radiation spreads out over a larger area. We will actually do a formula called the surface area heated on the Sun Angle Lab to compare why the direct sunlight is more powerful than the indirect sunlight. Now I'm going to go back a couple of slides here that shows that what we end up seeing is the point that is getting direct sunlight changes by time of year. On June 21st, the place that gets direct sunlight is the Tropic of Cancer. On December 21st, the place that's getting direct sunlight is the Tropic of Capricorn. Cancer is 23.5 degrees north. Capricorn is 23.5 degrees south. During March 21st and September 21st, which is the beginning dates of fall and spring, the sun's rays return back to the equator. It's the migration of the sun's perpendicular or direct sunlight as the Earth revolves around the sun is what determines what time of the year it is. So now I can go back, and I'm now going to kind of redirect you. This is where we left off. The solstices are the times of the year where each hemisphere is tilted the most towards or away from the sun. So in June, it's the northern hemisphere's 3 months to get direct sunlight or more direct sunlight, and in December, that's the beginning of when the southern hemisphere. And these are the times of the year when we get our maximum and minimum solar radiations for the different hemispheres. So here would be the summer solstice, and that's the time of the year where the sun's direct rays migrate the furthest north to the Tropic of Cancer. During the winter solstice, the sun's rays migrate their furthest south to the Tropic of Capricorn. So we basically talk about these direct rays as the subsolar point, and depending upon what season we're talking about, the subsolar point moves or migrates almost like a wild animal. And so that's one of the key things for us to understand, is that the sun's rays and the way the sun is positioned in the sky does change by time of year. Many anthropologists argue that's why the pyramids, you talk about the pyramids in Egypt, you talk about Stonehenge, you talk about Cahokia Mounds at Cahokia State Park in Illinois with a pole. They used wood poles that early primitive civilizations actually were attempting to track by putting up monuments that would actually line up with the sun at the certain times of the year. So a good little exercise for you would be to put the summer solstice at Stonehenge, and you will actually see celebrations that show on June 21st that the stones at Stonehenge actually do frame the sun, the summer solstice sun, to actually come right in between some of the rocks. And it's kind of a fascinating video if you were to do Stonehenge on summer solstice and hundreds of people gather. And it's been known at other places around the world that many monuments do line up with the sun at different times of the year. I would expect that you would be able to recognize that this is the summer solstice. On the summer solstice, the spot on Earth getting direct sunlight is 23.5 degrees north, and that's where you would get maximum solar radiation. And on this date, this would be the date of the year when the northern hemisphere would get its maximum sunlight, and it would get its most direct, highest sun angles. And above the Arctic Circle, above 66.5 degrees, people in northern Alaska and in Greenland, they could tell you the first day of summer, because as the Earth sets and spins, they would get actually 24 hours of daylight above the Arctic Circle. So there are specific areas on the Earth in latitude, and I will note that as part of your Sun Angle Lab, you will learn how to measure latitude from 0 at the equator to 90 degrees at the North and South Pole, that there are certain lines of latitude that people live in these areas. They can simply look up at the sun in certain times of the year. They could literally tell you what season it is just by looking at the sun and how it's shining or not shining on that given day. So you should be able to recognize, even if these labels weren't here, this would be the summer solstice because the northern hemisphere is tilted towards the sun, and you would know that this is the winter solstice because the southern hemisphere is tilted towards the sun. So on the equinoxes, it's an interesting time that the sun's rays return back over the equator, and that's the time of the year when both hemispheres share equally daylight and sun angles between northern and southern hemisphere, because the subsolar point is back over the equator, and the equator's designation is 0 degrees for the subsolar point. So there's an orientation of the equator and how solar radiation is equally being shared, and here would be a summer solstice, and here is the winter solstice. And you that effectively, because the Earth's tilt at different times of the year, the sun angles either shine directly in some places or they shine obliquely or indirectly. Around the equator, you're going to find that the sun stays much closer to being direct most of the year, and that's why it stays perpetually warm for all the seasons. The poles, they tend to perpetually get oblique or very low sun angles, and that's why they're perpetually cold. Whereas when you live where we do, we spend part of the year getting a mix of more direct sunlight, and then we have distinct seasons where we have very low indirect sunlight, and that's why our weather changes so much. So because of time here, I'm going to wrap up the lecture, and I will let you read the other slides, but I'm going to foreshadow the Sun Angle Lab is the ultimate sort of a challenge for you for this chapter, and I wanted to show you some key videos for you on the Sun Angle Lab that you might want to look at and prepare for to get ready for the exercises when you get into your course. I'm waiting for it to load, and I'll be done here shortly. My internet's running slow. I have a couple of videos here that I would strongly recommend you to look at under the Module 1 readings and assignments for Chapter 2. We will have some math to understand and calculate the sun angle and the intensity of that sun angle, and to show why people that live near the equator really do have and get more solar people, let's say, near the poles. I'm trying to get the module reading. Here they come. And I would strongly advise you to scroll down, and I do have 2 short videos. These 2 videos here under the seasons, I would strongly you to, or no, not those 2, under Chapter 2. These 2 videos under Chapter 2, linking math to the seasons and what causes the seasons. I would strongly recommend you watch these 2 videos, so they will help you prepare for the Sun Angle Lab to understand the concepts you'll need to calculate sun angles and the surface area heated of the different sun angles. Okay, that is the end of Chapter 2, and hopefully I was able to help you get through some of the key concepts here.